My name is Megan James, and I will be discussing the Cope elimination reaction. The Cope elimination is similar to an E2 reaction. In this reaction, a tertiary amine is oxidized to form an N-oxide intermediate. The moderate oxidizing agent is usually a peroxy acid, such as H2O2 or MCPBA. The oxygen from the N-oxide intermediate acts as a base to then form an alkene. This reaction is specifically unique to tertiary amines, so if you are going to perform this reaction, you must begin with a tertiary amine. After the reaction has occurred, your product will typically be in a less substituted position, which follows Hofmann's elimination rules. Now let's take a closer look at the mechanism. As previously mentioned, if you're performing a Cope elimination, you must start the reaction with a tertiary amine. In step 1 of the reaction mechanism, a moderate oxidizing agent will be added. In this example, H2O2 is added to oxidize the tertiary amine to form what we call an amine oxide. When we look at the amine oxide intermediate, it is important to note that the oxygen ion will be our base for this reaction. The amine oxide will deprotonate the hydrogen on the least substituted beta carbon. This is because the hydrogen on the least substituted beta carbon is more accessible. Another reason is the buildup of a partial negative charge in the transition state. This means the least substituted beta carbon will have a more stable transition state and therefore a lower activation energy, as opposed to its more substituted beta carbon counterpart. This deprotonation will form the pi bond on the alpha carbon, causing the leaving group to pop off. The major alkene product formed will be on the less substituted position. Let's continue and take a look at the reaction coordinate diagram for the Cope elimination mechanism. The reactants are indicated by red, the transition state blue, and the products green. The dashed lines in the transition state indicate the bonds breaking and forming to produce the product in green. If you look at the table on the right, you will see how the delta H was calculated. To calculate the delta H, the bonds breaking were subtracted by the bonds forming, which produced a negative difference. This means that the reaction is exothermic because the delta H is negative. The delta S was determined to be positive because of the increase in entropy from the reactants to the products. Using these two pieces of information and the Gibbs free energy formula, we can determine that the delta G is negative. And when you have a negative delta G, the reaction is spontaneous. Some ways to speed up this reaction can be to decrease the polarity within the solvent. This works because the mechanism is highly sensitive to solvent effects. Also, increasing the temperature and increasing the base will speed up the reaction rate as well. The use of the Cope elimination reaction can be found in a recent literature study conducted by Dae Kang and Justin Kim. The goal of this study was to find more bioorthogonal reactions. Bioorthogonal reactions are important as they provide ways to visualize, isolate, and manipulate biomolecules both in vitro and in vivo. Also, the development of these reactions are necessary as they help us study biomacromolecules, such as proteins, fats, and lipids. To achieve this goal and produce a bioorthogonal reaction, transformations were explored, density functional theory calculations were performed, and kinetics experiments validated the mechanism's overall reactivity. After experimentation, the retro-Cope elimination mechanism proved to be the most promising to find a bioorthogonal reaction. The bioorthogonal reaction between N,N-dialkyl hydroxyalamines and cyclooctanes is conducted. This reaction has a second-order rate constants, prime regioselectivity, and small reaction components. Overall, this experiment was successful and a new bioorthogonal reaction mechanism was formed. These are my references. Thank you for watching.